In this segment, we look at the reaction known as Fischer Esterification, which is going to be a way to go about taking an alcohol starting material along with a carboxylic acid, having that COOH functional group, treating it with an acid catalyst, and enabling the production of an ester as the final product of this reaction by linking that alcohol molecule to the carboxylic acid. So let's take a look at that reaction in more detail here. So we'll start with this problem where we have our alcohol plus a carboxylic acid and an acid, which we expect that combination of functional groups to give rise to an ester as the final product. We're going to walk through the process of how to go from these starting materials to the ester product using a mechanism to illustrate how this process takes place. So let's go ahead and do that. The first step, since we have acid present as our catalyst, is certainly going to be protonation. And so the particular atom that we are going to end up protonating here is going to be the carbonyl oxygen, because that is going to give way to the forward reaction making progress toward our product here. Protonate any of the other oxygen atoms would not enable us to make forward progress toward our product. So we will plug the proton on to our carbonyl group to make progress onward to our product of this reaction. So we'll go ahead and show that intermediate resulting from the protonation step. So we took the lone pair electrons from the oxygen and we formed a bond to that proton, which I'm showing in red. Then what happens as a result of that protonation is that the carbonyl carbon becomes much more positively polarized due to the fact that that oxygen now would have a +1 formal charge on it, and something that is positively charged is going to be much more electron withdrawing than something that has no formal charge. So therefore that oxygen atom is now very, very electron withdrawing. It's pulling electron energy very strongly away from the carbonyl carbon, making that carbonyl carbon very positively polarized. And what we know about positively polarized carbons is that they tend to be very, very excellent electrophiles. So now that we've done that protonation step, we've enabled the creation of a very electrophilic carbon. That's going to be the most electrophilic carbon in this reaction mixture at the moment, is that carbon right there. So what we'll do is then take the alcohol, and the alcohol can act as a nucleophile due to the fact that it has a lone pair of electrons on the oxygen. So we'll use the lone pair electrons from the oxygen to come over and attack that positively polarized electrophilic carbonyl carbon. At the same time that that happens, we would also need to push the pi bond electrons from here up onto the oxygen to avoid going over that tet rule at that carbon. And that's certainly something that we can do. We saw that happening when we were doing the reaction of Grignards with carbonyl groups, was that the Grignard reagent would act as a nucleophile, attacking the electrophilic carbonyl group. At the same time, the pi bond went up onto the oxygen. So similar thing here, except rather than using a Grignard reagent as our nucleophile, we're using an oxygen atom as our nucleophile here. So let's go ahead and draw out the intermediate that would result from this. And I'm going to try to color code this relatively accordingly to what we've seen up top there, in that my carboxylic acid structure, the portions derived from that, I'm going to put in black, like so. We had that proton bonded up here, and now we have an extra lone pair set of electrons there that moved up there from the pi bond, so I'll put that in. Then carrying onward to copy in the rest of this material, we created a new bond between the oxygen of the alcohol and this carbonyl, what was the carbonyl carbon, so I'll put that in red. Our oxygen that's bonded to that, I'm going to put in blue, just as we had it color-coded up top. So blue oxygen, one set of lone pair electrons, 2 carbon chain directly bonded to it. We've got the proton attached there, and this oxygen would then have a positive formal charge on it. So this should account for all of the electrons and atoms that we had going into this step. And for those of you that like to have a name to describe the reaction step, I'm just going to plug this in as step 2. The alcohol nucleophile attacks the carbonyl group, which would be our electrophilic carbon. Then at this point, what happens in the third step is a proton transfer. And the net effect of this proton transfer is that we need to protonate this hydroxy group and deprotonate right here. And so one way to go about showing that, there are multiple correct ways of doing this, but one way to go about showing that is to take the lone pair of electrons from the oxygen here and use it to grab the proton right here. So let's do our electron pushing arrows to show that method of proton transfer. So we're transferring the proton as the net effect from one oxygen atom to the other. So the oxygen right here uses its lone pair of electrons to grab the proton from here. So we'd classify that oxygen of the hydroxy group as our base, and down here our proton donor or our acid. So when we grab the proton from down below here, we need to break that oxygen-hydrogen bond, and the electrons from that are going to go onto the oxygen. So let's go ahead and draw the intermediate that results from the electron pushing arrows that we just showed here. So we go ahead and show our lone pair electrons all around just for purposes of keeping track of everything. Our oxygen right here, directly bonded to a 2-carbon chain. It had one set of lone pair electrons to start with right here. Now it's going to have a second set because we broke this oxygen-hydrogen bond and took the electrons from there and plugged those onto the oxygen. So we go ahead and do that. And then the OH group right here will have become an OH2 group because we took the lone pair of electrons from the oxygen and formed a new bond to hydrogen right here. So therefore we'd have OH2 with a positive formal charge. And now this is looking a little bit more like some things that we've seen before, hopefully, in that we have now a water leaving group. We've seen water act as a leaving group in a variety of contexts in this chapter, namely in those nucleophilic substitution reactions, and that's what's going to happen next, is that the water leaving group is going to leave as the carbonyl group, carbon-oxygen double bond rather, reforms. So lone pair electrons come down to make a carbon-oxygen double bond at the same time as the leaving group leaves. The water breaks away. This is really facilitated by the fact that that water is going to be a very stable, very happy to go leaving group. So we'll go ahead and draw out what would result from this in terms of what's going on with the organic molecule. We had an OH group up top there, and one of the two sets of lone pair electrons in it came down to make this carbonyl pi bond. That carbonyl group is directly bonded to the methyl group right here, which corresponds to that guy. It's also directly bonded through to here, so we need to go ahead and draw that up top as well, which I'll go ahead and do. Oxygen bonded to a 2-carbon chain, 2 sets of lone pair electrons on the oxygen. And remember to put your positive formal charge on our OH there, because our oxygen there would have 3 covalent bonds and 1 set of lone pairs, thereby giving it a positive formal charge. Now, if you want to go back and describe step number 4 of the mechanism in words, we could call that water leaves as the carbonyl group reforms. Then finally, we're almost to the final product here, because all we need to do to go from our intermediate that we have shown up there in the upper right to our final product is a deprotonation step. The acid here acts as a catalyst, meaning that it was consumed at an early step, the protonation step. At a much later step, step 5, we're going to reform that catalyst by doing a deprotonation step. In other words, we're going to remove a proton from the organic molecule, hence deprotonation. So the way that we can do that is using whatever base we choose. We have water sitting around there. Water is a very capable base. So water is going to come in, act as the base, grab that proton right there, forcing the oxygen-hydrogen bond to break to give us our extra set of lone pairs on the carbonyl oxygen, and leaving us with our ester final product. So in this reaction, we're demonstrating how we can take a carboxylic acid plus an alcohol and convert it into the ester product shown here. So what you will notice if we take a look at this mechanism, or any mechanism for Fischer esterification, is that you will observe that the O-alkyl group matches the structure of the alcohol. So the structure of the alcohol here, if we're trying to decipher the relationship between the reactants and product, the O-alkyl group here matches up with the O-alkyl group of the ester in the final product. So if you didn't want to write out the whole reaction mechanism to get to the product, what you could do is simply replace the OH group of the carboxylic acid with the O-alkyl group of the alcohol, and that would give you the product of this Fischer esterification reaction. based on the mechanism that we see here. Now let's go ahead and do a special type of Fischer esterification reaction that's going to be an intramolecular reaction. Intra, meaning within the same molecule, we are going to have the alcohol functional group and the carboxylic acid functional group to get reaction of those two groups within the same molecule to give us a ring in the final product. So we're looking at an intramolecular Fischer esterification. So the term intra that we see here is referring to the two functional groups that are reacting, that is the alcohol and the carboxylic acid are parts of the same molecule, rather than, in contrast to the example we saw just a couple minutes ago, which we would describe as an intermolecular Fischer esterification, where the two molecules are coming together from two separate sources, two separate molecules, and joining together in this Fischer esterification. Here, the two starting functional groups are present in the same compound. So let's take a look at the example problem here, and we'll try to write out the mechanism for this to work our way to the product that we would expect. As always, if you want an extra challenge, try to work through this on your own and then take a look at the solution to see how you did. First step of the mechanism, as we saw before, was protonation of the carbonyl group, because that's going to enable us to create a more electrophilic carbonyl carbon right here to get their reaction going. And that's really how this proton is able to act as our catalyst here. So we take the lone pair electrons from the carbonyl group, bring that over to grab the proton from whatever acid we are using, and write out the result of this protonation step here. So we're doing protonation as the first step of the mechanism, just like we did in the intermolecular reaction, except we're doing this intramolecularly, all within the same molecule here. Now, at this point, what we saw in the last example, we've created a very electrophilic, very positively polarized carbonyl carbon. So I'm putting that delta plus on it to indicate that that is where we're emphasizing as our positively polarized carbon atom. It's positively polarized because it's bonded to two electron withdrawing oxygens. This one up top is particularly electron withdrawing because it has that positive formal charge, which makes it very, very hungry to have electron density come toward it, because it's very electron deficient if it has a positive formal charge. So what's going to happen is that the oxygen atom over here from our alcohol group, because if we look at the different parts of the molecule, we could decipher an alcohol functional group and a carboxylic acid functional group at opposite ends of the molecule. The alcohol functional group is going to come over, acting as our nucleophile, and it is therefore, in meeting the definition of a nucleophile, going to attack our electrophilic carbonyl carbon, forcing the pi bond electrons up onto the oxygen. So let's go ahead and draw the result of that step 2 of the mechanism, where the nucleophile attacks the electrophilic carbon. Now, in this reaction, what you will notice is that due to the intramolecular nature of this reaction, where the oxygen is coming around and attacking a carbon within the same chemical structure, what's going to happen is we're going to create a ring system. And that's a hallmark of these intramolecular esterification reactions. They end up creating esters that are part of rings. So let's go ahead and decipher what ring product is going to result from this. And in order to accomplish this, I recommend coming up with a numbering system or some way of recognizing what each of these carbons are so they can track out where it's going to be. So I'm just numbering, starting at the carbonyl carbon, 1, 2, 3, 4, and I'm even going to number the oxygen atom so that we know where to put who here. So 5 carbon atoms, and atom number 5, oxygen atom number 5 that is coming around to attack carbon number 1. And so what's going to result here is the production of a 5-membered ring, because we can think of this now, once we form that bond that we're showing in red, as a continuous system here, or a ring. See how it connects back to itself. And so therefore, what I'm going to do is draw a template of a 5-membered ring and then fill in my atoms. So go ahead and fill in a 5-membered ring. I'm going to number that 1 through 5. It doesn't matter how you number it, as long as you number it in order 1, 2, 3, 4, 5. I could have numbered clockwise, counterclockwise, doesn't matter at all. You'll end up with the same product one way or the other. I'm going to fill in the appropriate atoms and groups at each of those 5 positions based on the diagram that we have up top. So at position 1, that was where Up top, we saw that we had the hydroxy group bonded over here. So I need to fill that in. And also at position 1, we had what was the carbonyl group, but is now just an OH group due to the fact that the carbonyl electrons went up onto the oxygen. We come on over to carbon number 2. At carbon number 2, we have a methyl group directly bonded right here. So I'll go ahead and plug that in. Carbon number 3, don't see anything going on there. It's just a straight up CH2 group, so I leave that as. Carbon number 4, same thing in our original structure. And we come onward to number 5. Number 5 was actually an oxygen atom, so I need to fill that in here. So there's no carbon at position 5, instead it's an oxygen. So I went ahead and filled in that oxygen atom there at spot number 5 of our molecule. And at spot number 5, that was where we linked back to carbon number 1, so that makes absolute sense here that position 5 links to position 1. At position 5, we have a lone pair of electrons up top here, so we'll go ahead and plug those in. Our other lone pair of electrons down below here was what formed that black covalent bond in the ring, so we don't show that, but we do need to show the proton is still hanging out there, and as a result, position number 5, that oxygen atom is going to have a positive formal charge on it. So now, at this point in the mechanism, what we will do, much like what we did in the intermolecular reaction mechanism we looked at before, is we need to create water as a leaving group. And in order to do that, we have to do a proton transfer to transfer a proton onto one of the 2 red hydroxy groups in our intermediate here. So to accomplish that, we take our lone pair electrons from our oxygen, use those as our source of electrons to make this enable to be a base. Come over, attack the proton from here, break that oxygen-hydrogen bond like so, and that's going to lead us to our protonated intermediate. So we'll go ahead and trace out our 5-membered ring with that oxygen atom in it. Oxygen is now going to have 2 sets of lone pair electrons. We did 1 set already, and we picked up a second set when we broke that oxygen-hydrogen bond. So we go like so. Then we come up to here, and we had 1 hydroxy group that nothing has happened to. The other one is going to have become protonated, so we go ahead and put OH2 in there with 1 set of lone pair electrons. That would result in it having a positive formal charge, and at position 2, don't forget atoms along the way, we still have that methyl group hanging out there. So now, at this point, we have an excellent leaving group, that is our water, H2O. And so, with that in place, we'll break the water away, like so, and to create the most stable structure possible, bring the lone pair electrons from that oxygen down to make a pi bond at the same time you break the leaving group away. So we'll go ahead and draw out the intermediate that results from that step that we just saw there. So we'll have our OH like this, and plug in all my lone pair electrons. Now we are very, very close to the final product. To make the final product, we need to recreate the catalyst. We need to recreate acid and deprotonate. So to do that, we take our oxygen lone pair electrons, bring them over to grab this proton here, deprotonating that oxygen. That results in breakage of the oxygen-hydrogen bond like so. And that will allow us to go ahead and get this rolling. So we have our carbonyl group right here, methyl group still hanging off the side, and H3O plus if we want to go ahead and dot all our I's and cross all our T's here. Now the type of functional group that we've created here at the end, we could certainly refer to as an ester because of the fact that we have a carbonyl group directly bonded to an oxygen, and that oxygen is directly bonded to another carbon atom. In addition, we could also more specifically refer to this type of functional group as a lactone. A lactone is an ester that is cyclic. So a lactone equals synonymously with a cyclic ester. So you'll notice that the oxygen atom of the ester is part of the ring system, and that's going to be the hallmark of a lactone, is it has the carbonyl group coming off of the ring and the oxygen atom of the ester, the single bonded oxygen, as part of the ring, making these lactones so-called cyclic esters. So with this information now in hand, you should be comfortable with either doing an intermolecular Fischer esterification reaction or an intramolecular Fischer esterification reaction with any combination of carboxylic acid and alcohol reactant.